Hello everyone, my name is Aline Cotel. I'm a faculty member in civil environmental engineering at the University of Michigan. So I just want to talk a little bit about the kind of work I do. So my area is fluid dynamics. I look at biological system as well as environmental systems. In particular, the topics I'm interested within the whole area of fluid dynamics are mixing and turbulence, especially in stratified flows. And some of my work beyond fluid mechanics has been also trying to help with capacity building for women engineers and scientists. You can find more info on my webpage. I just put a few pictures of the kind of some of the projects I've been involved with. So a few years ago, I lived in Canada and I had tried to embrace the weather. And I looked at heat transfer on face when people wear Inuit clothing. So that was a lot of fun. We did some experiments in wind tunnel and tried to understand how the fur is really protecting people's faces in really harsh climate. We've also done work, here's the boat at the bottom left, looking at wave impact in marshes and general shores in the upper Great Lakes. So looking at, fish distribution, fish habitat in kind of wavy environment created by a lot of boat traffic. We've also done some work, and I'll talk about this in a second, on fish habitat in rivers. So here is me snorkeling, trying to find fishes, and then trying to understand again what are the fluid factors that affect where we find fish and not. And then I've also done some work at stratified flow. So this is a jet impinging on a stratified interface, and again looking at mixing and turbulence. That can also be applied to things like this. So stratified flow theory can also be applied in some cases to rotational flows. So here's an example of a wingtip vortex at the end of a crop duster. So just to show you that sometimes some of those theory can have far-reaching impact beyond just that specific area you're working in. And here's another stratified flow example of a gravity current on a slope. So if I look, just give you a little bit more insight into the work I do in biological fluid dynamics, what we're really trying to understand is how fish and turbulence interact, especially when we're thinking about how that changes the swimming ability of fishes, how they choose their habitat. In some cases, people have found that turbulent eddies can help fish perform better. So in terms of swimming and migration, that can have lots of impact. So we do field work as well as lab work. So here's some example of some of the field work on shore that we've been doing. Here's some work in a river. And we do point measurement as well as kind of planar measurement of the physical parameters. So velocity, vorticity, calculate circulation from this, looking at turbulent kinetic energy, all this kind of stuff. So hopefully that gives you a sense of this type of work. I'm just keeping things very general, and I'm happy to answer questions during the school. You can contact me directly. Always happy to talk about this stuff. Here's another example that's recent, just finished a couple years ago. Is looking at spawning reef in the Detroit River. So there used to be a lot of sturgeon in this whole Lake St. Clair, Lake Huron corridor, and they've mostly disappeared. So there's been a lot of effort in trying to restore habitat for those sturgeons. And so the key is to create reef where they can spawn, so they can drop their eggs in the cracks between the rocks, and then hopefully the population would rebound. And the project here was to figure out what is the shape of those reef. And so we did some measurements with looking different little gravel in a flume and trying to see how the shape affects the flow conditions, because that would affect how a sturgeon would actually use the reef for spawning. So here's an example of the velocity profile for different shape, or here's shear stress profile. So you can see there's quite a big difference between the shape of this artificial reef versus other shapes. So here's a cool picture of what the flow looks like just above. So within the boundary layer, you get this rough boundary layer going on above the reef. So again, just to give you a little taste of things, and I'll just finish with biofuel mixing. So we were interested in looking at how biofuel, if there were a spill in the environment, how that mixes with surface water, so a lake or a river. There's been cases of biofuel spills that killed lots of fishes, tens of thousands of fishes in different environments. There's very little we understand how biofuel mixes with water because it has a nonlinear component. So here's some example of very simple experiments we did trying to understand the mixing. So here the pink fluid is the mixed fluid between this biofuel mixture and water. There's a lot of cool interfacial instability that you see at the interface between the biofuel and the water. And so we try to characterize how much mixing happens for different type of nonlinearity. So this parameter here, this buoyancy reversal, really tries to quantify how much nonlinearity there is in the system. So this is my little very quick summary of some of the work that I've been involved with over the years. And like I said, I'm happy to talk to any of you about this during the school or beyond the school.